Everyone, welcome to another episode of Science and Technology Q&A about, no, I'm sorry, this is about history of science and technology Q&A. Let's see, I see a number of questions saved up here. There's one from Anon. Can you talk about the history of pi? Well, let's see what I can remember. Remember pi ratio of the circumference to diameter of a circle. For any circle, the answer is 3.14159, ... I think the Babylonians already had some idea of pi. People were using approximations to pi. The first sort of big approximation to pi was 22/7. The development of use of pi got gradually more accurately computed. For a while in Europe, it was called Ludolph's constant, because there was a chap called Ludolph who'd computed it to, I don't know, 6, 7, 8 decimal places, something like that. The name pi, I believe, came from a chap called Jones, maybe a William Jones in England. But it was really adopted by Leonhard Euler in the 1700s. And that led to, so Euler introduced, well, several pieces of notation, much mathematics, several pieces of notation. Euler was a prolific mathematician. I have a copy of his collected works. It's a whole shelf of things. I think they're all in Latin, at least mostly in Latin. It's kind of interesting to look at Euler's collected works because the formulae look completely modern. And, you know, the text is in Latin, but he had all the sort of notation of calculus and so on pretty much in its modern form, including pi. And he also introduced the notation E for the exponential constant 2.718 and so on. Somewhat confusingly, people sometimes call that Euler's constant, which is really not what is correctly said, because Euler had a different constant, usually called gamma. It's about 0.577, that is called the Euler's constant or the Euler-Mascheroni constant. And that's the thing that you get if you take the sum of 1 over n going from 1 to infinity. That sum diverges, but the sum is roughly diverges like log n, and the difference from that to log n is this gamma constant, which shows up in a bunch of places. It's not nearly as common as the exponential constant, but it's still pretty common. And that's the thing that in the mathematical literature is correctly called Euler's constant. So about pi. Well, in what to say about the computation of pi? Well, then these computations, well, there's a few things to comment on. One is people started computing digits of pi. They seem kind of random, 3.141592653. That's as far as I know it. People wondered, were the digits of pi random? Were the digits of pi such that, for example, every digit written in base 10 would occur equally often? So 1, 2 through 9 and 0 equally often or not? Would there be a run of zeros, a huge run of zeros in the digits of pi that was more than you would expect based on sort of randomly picking digits? Nobody knew. The first question was, well, for example, would it turn out in the end that pi was a rational number, just a ratio of integers? It was known fairly early that it was not. I'm trying to remember when that was first known. The square root of 2 famously was proved to be not a rational number by Pythagoras and his followers, something which kind of surprised them at the time, 5th century BC or so. But the proof that pi is not rational must have come much later, but I'm not sure exactly when. The next question was, could pi be represented as an algebraic number, as some square roots, cube roots, 15th roots, whatever else? That was, I think, established in the sometime in the late 1800s. It was established that pi wasn't an algebraic number, that you couldn't write a kind of formula, a polynomial equation whose solution was pi. Then the question, well, how do you compute pi? How do you get kind of a good, work out the digits efficiently, there was a chap called Gregory, who I think was a contemporary of Newton or soon after Newton, who had a series for pi. One of the things that came out from what Newton did was the idea of power series, the idea that you can approximate a function by giving a constant term, a term proportional to x, x squared, x cubed, and so on. It's kind of the analog for functions of having a number be approximated by some number of, let's say a decimal number, the digits after the decimal point. There's some number of ones, some number of 1/10, some number of 1/100ths, and so on. So a power series is like some number of x's, some number of x squareds, and so on. And one of the power series that got worked out was the power series for the arctangent function, and arctan of 1 is pi over 4. And so if the series for arctan was worked out, I think it's usually called Gregory's series, and it has various coefficients that can be worked out. That's a way to work out the digits of pi. And that was sort of the common way to work out the digits of pi until, well, another development was Ramanujan. This is around 1910-ish time frame. Ramanujan was a prolific generator of mathematical formulas and results, initially working in India, later sort of brought to Cambridge by G.H. Hardy. But Ramanujan, kind of his secret weapon was that he was a good calculator, and he would just work out lots of kinds of things, and then he would sort of guess what's the exact formula for this. And he had great intuition, and usually he got it right. One of the things he noticed was that e to the pi square root of 163, I think, is very close to an integer. Okay, most people would just sort of said, so what? But he actually realized that that was a significant thing related to elliptic functions and so on. And he also realized that it was a thing that could be used to compute digits of pi. And actually, Ramanujan's method for computing digits of pi was sort of a leading method for computing digits of pi, well, even now, but until recently. So that then, when electronic computers came on the scene, people started using them to compute digits of pi. So even in the late 1940s, people were using the very first electronic computers to compute digits of square roots of 2 and things like this, and digits of pi. Then they were very curious about this question about how random were the digits of pi. Was pi what was called a normal number, in the sense that every digit occurred with equal frequency and every block of digits occurred with equal frequency? So a bunch of tests were made. Some of the earliest sort of experimental mathematics done on computers were made of that question. And then kind of, I think, by the 1960s, sort of the race was on who could compute the most digits of pi. A friend of mine, Bill Gosper, held the record for a while using Ramanujan's method for computing digits of pi. I think that was, he had the record maybe in the 1980s. Then it passed to a chap in Japan, and it's kind of gone back and forth. Some other friends of mine, David and Gregory Chudnovsky, held the record for digits of pi for a while. They actually built a special purpose computer to compute digits of pi. And people kept on computing digits of pi, and it kept on seeming like the digits of pi that were coming out were completely random. There was no sort of statistical regularity that could be found in the digits of pi. Then one thing that came on the scene in the 1990s, early 1990s, was the following thing. So it had kind of been assumed that if you want to compute the millionth digit of pi, you have to compute all the digits up to the millionth digit of pi, that you couldn't kind of jump ahead and compute a digit without computing earlier ones. Then on the scene came a chap called Simon Plouffe. Simon Plouffe, sort of an interesting character. I haven't seen him for a few years, but he was a very self-taught mathematician in Canada who, among his other kind of interests, he got very interested in kind of patterns in numbers and things like integer sequences. There's a chap called Neil Sloan who had written a book called The Handbook of Integer Sequences. And it was published as a book in the I think originally 1960s or early 70s. And Simon Plouffe took it upon himself to hand type in the Handbook of Integer Sequences, and later collaborated with Neil Sloan, who didn't have it in electronic form like that. But Simon Plouffe then noticed something about the digits of pi. He noticed that there was a formula you could give that would tell you what, as he thought, the nth digit of pi, any digit, nth digit of pi in base 16. And it's a funky formula, and it has a limited set of terms that allow you to compute that digit without the ones around it. Actually, it's an easier case for computing digits of log 2 in, I forget which base, maybe even base 2. I can't remember. But anyway, so this was something which kind of was a very weird thing. And Simon Plouffe was not sort of well knowledgeable or educated in kind of higher mathematics, bit like Ramanujan. Actually, Ramanujan, I think, was more educated in those kinds of things, significantly more in some areas. But then Simon Plouffe ended up working with some mathematicians in Canada to sort of at least publish this statement about the nth digit of pi. And as the Borwein brothers were the main people he worked with. It's a little bit of a complicated story because it isn't quite right that you can just parachute into the nth digit and compute it. It relies on the fact that some carry digits, like a carry digit like you get if you get to 0.9999999 and you add a tiny number, then it'll flip over to being 1.000, and there's a big long sort of carry that happens. The result about the nth digit of pi kind of depends on a sort of statistical statement about there not being too many of those carries that build up. And I'm not sure whether the level of ability to actually prove that is. I suspect to be able to prove it, you have to be able to make statements about the digits of pi. If you can assume that the digits of pi are random, you can establish that the probability of a problem there is sort of arbitrarily small, but perhaps not zero. So that's a little bit, let's see, what else to say about the digits of pi. I am reminded of kind of a fun story about the digits of pi that is a science fiction story about the digits of pi. So there's a movie called Contact, an alien first contact movie. There's a book by the same name written by Carl Sagan. And one of the things that happens in the book version is, okay, the aliens have been contacted, the humans are interacting with the aliens have built this amazing kind of network of interstellar sort of transportation kind of tunnels or something. And the humans are saying to the aliens that these transportation tunnels are to the humans really amazing. So they ask the aliens, what's amazing to you guys? And the aliens say, well, we computed the digits of pi, we computed a very long way in the digits of pi, and eventually, somewhere in the digits of pi, we found, they said, a picture of a circle. And they said, that's sort of an amazing thing to us. Now, that claim is sort of philosophically broken. I mean, it's an amusing science fiction kind of idea, but the question is, what could that possibly mean? I mean, the digits of pi are something abstractly determined. The fact that you find something you recognize in the digits of pi is much more on you than it is on the digits of pi. It's also kind of worth realizing as you sort of unpack what that could possibly mean, that you could say, well, how could the digits of pi have anything that means something in them? They're just abstract digits of pi. Well, you could say the same thing about the universe, because if it's true, as I'm pretty sure it is, that there's sort of a computational process that generates the universe, it's being generated much like the digits of pi are being generated. And we are sitting here kind of doing what we're doing and being on this live stream and so on. And we are like the quintillionth digit of something like pi. And that's what our universe is, so to speak. And so insofar as we find something meaningful in what's going on in the universe, that's happening by sort of us picking out the quintillionth digit of this pi-like thing that is the representation of what the universe is doing, and deciding that that's meaningful. And so that's kind of in that sense, it's kind of, you could live inside pi, and that's sort of what we're doing, except it isn't actually pi. It's something not quite like that, but it's a computational, the result of a computation. You know, one thing I've sometimes said is people searching for extraterrestrial intelligence in the universe, as the universe is, and it's like, is there something going on in the universe that we can identify as being meaningful and intelligent, as opposed to just being a thing that happens in nature in the universe? So it's kind of like we're searching for extraterrestrial intelligence. We're doing SETI in the universe. So one thing I've sort of had fun with a number of times is what I've called SETI among the numbers, which is, can one essentially search for the analog of extraterrestrial intelligence, but it's merely in the digits of numbers like pi? Is it possible to find things which seem to us meaningful in things like the digits of pi? What would that possibly mean? Well, for example, you might have some way, right now the digits of pi look to us random. We know in some sense they're not random because they are, after all, the digits of pi, the ratio of the circumference to the diameter of any circle. Well, there's a way to say what they are. It's not just saying it's digit, digit, digit. There's a way to summarize what they are. But once you've generated those digits, unless you knew that summary, they seem completely random. But is there perhaps some way of making them sort of seem less random, finding a regularity in them? To give you an example, something like square root of 2 is 1.414, et cetera, et cetera, et cetera. If you generate its digits, they look completely random. But if you generate not the digits, let's say in base 10 or base 2 or whatever else, but instead you generate the continued fraction of that is a different representation of a number. So a continued fraction, it's an idea actually from the 1600s. It's 1 over, well, it depends on how you set it up. But for example, 1 over a number plus 1 over and another number, and it's this stacked up fraction. And it turns out that the square root of 2, in fact, any square root has a continued fraction that repeats. So the most famous one is the golden ratio, square root of 5 plus 1 over 2, about 1.618. The continued fraction for that is just 1 over 1 plus 1 over 1 plus 1 over 1 plus, et cetera, et cetera, et cetera. It's all ones. And that's the continued fraction. I think for square root of 2, it goes 1, 2, 1, if I remember correctly, and just repeats 1, 2, 1, 2, 1, 2, et cetera. So that's a way in which there's sort of a regularity that you can find in a different representation for square root of 2. But the question is, if you just go exploring, let's say, digits, could you find a regularity in those digits? There's sort of this mismatch between numbers whose digits have regularity and numbers for which we can write down a formula for how to generate the whole number. So for example, any rational number, ratio of integers, its digits must repeat. So sometimes it's kind of a complicated repetition, like 1 over 81, I think is 0.0123456789 maybe, and then it repeats. So it's a fairly long repeat. In general, the period of the repeats for rational numbers can be quite long, but any rational number has digits that repeat. You could ask a question: are there numbers that, for example, go up in an arithmetic sequence, or have some regularity like that? Turns out there are some of those numbers, and they are. Oh no, I'm sorry. That's for continued fractions. The continued fraction, as I said, for a square root, it's always periodic. For something like e, it comes in kind of blocks. And if you for something like pi, the continued fraction looks quite random. The continued fraction, unlike digits that just go from 0 to 9, the terms in the continued fraction can be any integers. So pi has, I think, a 239 that shows up fairly quickly. So it's sort of an anomalously large continued fraction term that shows up. But in any case, there's no regularity that's been found in the continued fraction expansion of pi either, just like its digit expansion. It's worth saying that whereas the analog of having random digits in in a number written in sort of base 10 or something, for a continued fraction, there's a distribution of sizes of the continued fraction terms, and there's a thing called Khinchin's constant, which characterizes that distribution of sizes. And for something like pi, it kind of follows it's a random distribution of sizes for a continued fraction. Anyway, for continued fractions, you can have those terms in arithmetic progressions. You get things like Bessel functions as formulas in that case. But in the case of, in most of these cases, there's really a mismatch between numbers whose digits or whose continued fraction terms can be represented in a simple way and numbers for which there's a formula like pi or like square root of 2 or something like this. The one case that's kind of a different case is you can construct a number that has very regular digits, very regular sort of digit sequence, like, well, for example, a famous one is one called Champernowne's constant, which is 0.123456789 1011121314. So you're writing out all the base 10 integers in one after another, but treating them as pieces of the decimal part of a number. Or you can do the same thing in base 2. That was a thing that was invented in the 1940s by a chap called David Champernowne, who was at that time a student in Cambridge, a friend of Alan Turing's. In fact, they had constructed a chess computer together, or at least were talking about doing that. David Champernowne's number has the feature that every block of digits occurs eventually with equal frequency. But that number, while the digits can be represented fairly by that procedure, there's no formula for Champernowne's number. There's no, oh, it's given by some square root of pi times this or that or the other. There's no known formula for that number. David Champernowne himself went on to become a fairly distinguished economist in the UK after that time. Let's see. Susie is asking, oh, I'm being reminded here that, yes. So one thing that's fun with pi is there's a pi day every year, March 14th in the American way of writing out dates. It's 3/14, so it's like 3.14. Well, in 2015, there was a kind of pi day of the century because it was 3.1415, which are the next digits of pi. And of course, if you keep going, you could have a pi second of the century where you have the additional digits 3.14159, yeah, it was 9, it was about 9 in the morning. So happened in March 14th, 2015, there was a conference, trade show that was happening South by Southwest in Austin, Texas. And we as a company had kind of a presence there. And since, we make Mathematica and Wolfram Alpha and we do math things, how could we not celebrate the Pi Day of the century? So in one of those amusing corporate stories, I was talking to the person who ran our events, still runs our events operations. And I was saying we should get a big pie as part of our sort of celebration of Pi Day in Austin, Texas. And I forget I'd said that. A week or two goes by. We're in some other meeting. And it's like, well, I've called around all these bakeries in Austin. And it's like, what? What bakeries? Why are you calling bakeries? And unfortunately, this was one of these cases where the homophone pi, P-I-E, and pi, P-I, were kind of mixed up. And it was like, do we get a pie, like to eat, or do we get a big thing that looks like a Greek pie written out? In the end, we got both. And we also got some other fun things to celebrate Pi second of the century. It is interesting that this issue about pi versus pi, when we were first providing with Wolfram Alpha the kind of knowledge backend to Apple Siri service, that was one of the big issues, was we were getting streams of data which came from voice to text. And every time somebody would say the mathematical pi, it was coming out for us as PIE. And so that was the thing we had to deal with on the back end. Later on, we started getting homophone stacks where we were kind of getting the alternate what the words could have been, so to speak. In any case, that's just a little bit more on pi. Is pi still being researched today? Susie asks. Well, things like, is pi a normal number? Yeah, people would like to know the answer. That's a really hard problem. It's one of those problems where people will say in math, mathematics isn't ready for such a problem. We just don't have methods that will allow us to kind of really get traction on that problem. But I would say that certainly there are questions about pi like that one, which is still very much current questions. By the way, I mean, some people say, pi over 2 is really the constant we should be talking about, not pi. And that's sometimes written as a tau, which kind of looks like a pie with one sort of pillar on it. I did a study at one point of sort of the scientific literature asking the question, is pi on its own more common or is tau more common? Pi definitely wins. See, the thing that's interesting about something like pi is all the different places it shows up. It is the ratio of the circumference diameter of a circle. It's also many other things. Like, for example, pick two integers at random. Ask whether they are relatively prime. The probability of that is 6 over pi squared. Another place where pi shows up. There are just all kinds of places where sort of the mathematics that one wants to do kind of focuses somehow on this one concept. And that's a thing that's sort of interestingly common in mathematics, that there are these ideas that just sort of show up in many different places. I'm not sure we really understand why that happens. It's partly a matter of what's selected to be studied in mathematics, but it's something else beyond that. And I think it's sort of an interesting mathematical question. Why are there these sort of attraction points? Occasionally, people will define things in math where the definition sounded cool at the time, but it never shows up again. And then there are other cases where people define the thing because it shows up in something about how things work in the orbit of the moon or something, happened with Bessel functions. And then they show up all over the place. The kind of shapes of circular drum heads and things like this, which didn't seem like they had any connection to the first place it showed up, but there end up being these sort of attraction points of concepts that show up many times. Lausie is asking, was there always a connection between pi, pi, and PIE? I don't think so. I think pi was originally introduced by this chap Jones as a way of standing for the perimeter of a circle. Pi being, Greek letter that's the analog of P, that was like P pi for perimeter. That was the idea. A piece of sort of trivia along those lines, it's pretty common if you're sort of doing things in math, you might have, there's a quantity that's P, a quantity that you call Q, a quantity that you call R. Well, in the Greek analog of that is, well, there's a pi letter in Greek and there's a rho letter that is the analog of R, but what's the analog of Q? Well, it's actually a letter that kind of went out of fashion, so to speak, before the classical period in Greece. It's the letter koppa that it's kind of like, it actually looks a bit like a Q. And it's sort of fun. If you want to be kind of obscure and erudite in doing math kinds of things, then you have, PQR and pi koppa rho as things that you can use. Let's see. All right. There's questions here. There's one from Amrudo. Can pi be used for data compression? I don't really think so. I mean, when you make a code, for example, a stream cipher, sort of the typical way you do that is you say, I've got my message. I'm going to represent it as a sequence of binary bits, um, and then to encode it, I'm going to combine it with a random sequence of binary bits. And I'll do that by forming the exclusive OR of every bit. So that means that if the message has a 1 somewhere and the encoding stream has a 0, then the result is 1. If the encoding stream has a 1, the result is 0. It's always if the digits were different, the result is 1. If the digits were the same, the result is 0. And so then you send that result stream, that's your ciphertext. And it just turns out, you can see rather easily, the math works out. If you have that same encoding stream, then all you have to do is take that ciphertext, combine it with the encoding stream, and you get back the plain text. So plain text plus mod 2, the encoding stream equals ciphertext. Ciphertext plus encoding stream mod 2 equals plain text. So that's a way to do encoding. It's actually what's used after there's a certain amount of kind of exchange of keys and so on that happens using public key cryptography. Things like that, it's actually usually done with blocks rather than with a stream like that, but you can use a stream like that as a way to do encryption. And so you could imagine taking the digits of pi and saying, those are going to be my encoding stream. Of course, that's fine so long as nobody knows it's the digits of pi. But as soon as somebody tips off the enemy, so to speak, oh, they're just using the digits of pi, the game is up and the enemy can decode what you're talking about. So it doesn't really work very well for that. You really have to have a larger space of possible keys to determine the stream. I do wonder whether you could take some functions of pi and use that as a way to generate the encoding stream and have that work well. I don't think it's a particularly practical thing to do because it's actually comparatively difficult to generate the digits of pi. If you want to use a method like that, well, for example, one of the cellular automata that I've studied for a long time is a good way of generating a sequence of apparently random bits from a key. Technic comments, is the only reason that pi shows up more often than tau because we use pi more often. Well, what I was doing was I was looking at every occurrence of pi, and I was asking, what is the coefficient of pi? Is the coefficient of pi half, or is the coefficient of pi 1, or is the coefficient of pi 7? What is it? Does it usually show up as the halved version, 7 pi over 2, or does it show up as 7 pi? And the point was that it usually didn't show up as 7 pi over 2, so to speak. The actual times that tau is used as written in formulas is much smaller. This is the question of, if we were to use tau, would our formulas get simpler? Let's see. A question from Emrudo here about slide rules. So a slide rule, I have a slide rule somewhere here. Let me just see. It just might happen to be. Let's just see whether I'm lucky enough to have it in within reach. I think I'm going to lose here. No, it's not within reach. I'm within reach are all kinds of cool mollusk shells and so on, but no slide rule. Okay. I almost feel like going to get a slide rule just to, you know what? I think I'm going to do that just as something different. Hold on just one moment. Okay, a bit of show and tell just for once. Let me see here. Just want to set this up so that I can see what I am doing. There we go. All right. This is the slide rule. It is it's just like the one that I had. The one that I had, I'm afraid, has decayed somewhat. So there's a slide rule. And actually I had just picked up I was proud of myself for knowing where this was, but I just picked up two things that are from my ancient past, which are calculators. These are calculators that I had back in the early 1970s. Look, appropriately labeled with my name. I think until recently it switched on. That's a Texas Instruments scientific calculator, and I also had a Hewlett-Packard scientific calculator. The main feature of HP calculators I just mentioned is the whole reverse Polish notation, that you would say things like 2 enter 3 plus. You type a digit, you type a number, you push it onto the stack, you push another number onto the stack, then you give the operation afterwards. It's kind of a operand operator. That notation was kind of invented in mathematical logic in the 1920s or so by a chap called Łukiewicz, who was part of the kind of Polish school of mathematical logic. And his notation was more like forward Polish, usually, where it was operator, operand. So like plus 2, 3. It's a bit similar to the way that things work in Morphem language and so on. But reverse Polish was kind of like operand, operator, and it was called Polish by the folks at HP, I think, in sort of recognition of the school of mathematical logic. Okay, back to slide rules. Okay, well, this is set up correctly. Yes, this is a slide rule. I don't know whether you'll be able to see the scales on here, but the story the story behind slide rules, it goes back to a chap called Baron Napier, who was a Scottish baron who invented logarithms and invented these things called Napier's bones, which were a way to compute effectively using logarithms. So what's the idea of a logarithm? Well, you say something like 100 is 10 to the power 2, 10 times 10. 1,000 is 10 to the 3. 10,000 is 10 to the 4, and so on. And then you can ask the question, well, what's 514? That's 10 to the power something. Okay, well, if you know what it's that something is the log to the base 10 of 514 or whatever. The important feature is that multiplying numbers corresponds to adding logarithms. So if you're saying 10 squared times 10 cubed, what is that equal to? It's 10 to the power 2 plus 3. So you're adding the exponents, but the result of that gives you is telling you that the product of the numbers. So logarithms are a way to turn multiplication into addition. Okay, so how does that relate to a slide rule? Well, if you can see the slide rule, the main thing you do is there are lots of scales here that do all kinds of different things, but the two most important scales are the C scale and D scale. And what you do is you line up, let's see if I can set this up correctly. You line up, for example, the C scale, the 1 of the C scale above the 2 of the D scale. And then what will happen is on that part that's sticking out there, every number will be twice the number that is below it on the scale below. And you move this cursor along. And so, for example, I can move this so that I get to, where did I put this? There we go. Yes. So, for example, I get I'm saying it's slightly the wrong way around. The smaller numbers are on the scale that was sticking out here. So there's a 2 up above, and there's a 4 down below. There's a 3 up above, and then there's a 6 down below. And so that's the way it it was set up. So kind of the notion here is you can do multiplication just by the addition happens just by the fact that you have a piece that is the addition is just by the distance along this kind of ruler. I have to say one kind of funky personal story. When I was in kindergarten, actually, and I was sort of learning all these addition facts and things like this, I was kind of resistant to that. And I discovered that if you just took ordinary rulers and lined them up, you could do addition with ordinary rulers. Just the same idea as with a slide rule. I didn't know about slide rules at the time, but you're just doing it by having the scales on the rulers, and one of them you line it up so that you're adding to the other ruler. And so I think teachers of mine were often mystified why I had two rulers on my desk with some frequency, and it was an early use of tools to do computation. Anyway, with slide rules, back when I was a kid, at least, this was sort of the standard way to do computation, and we could get pretty quick at doing things this way. Now, the other scales here are things like there's a reciprocal scale. There is, oh boy, there's some scales I don't even recognize here. There are some, there's a scale that is actually multiplication by pi. And that's a useful scale. There's a scale that takes squares, a scale that takes square roots, and so on. The idea of kind of just lining things up and reading off the answer is their so-called nomograms are another kind of way of just sort of lining things up and reading off the answer from tables of numbers. Sometimes slide rules also come in circular form factors, but the more common kind was this kind. I think the slide rule was invented by a chap called William Outred, who was the same person as invented the multiplication sign. Multiplication sign was something somewhat controversial in its time. This is 1600s. This is, I guess, late-ish 1600s. People like Gottfried Leibniz sort of wrote these letters to Outred saying, the using an X for multiplication is just going to be incredibly confusing. People are going to, think that's a variable X forever. But of course, the multiplication sign did stick. Somewhat amusingly, the high school that I went to, Eton College, which was founded in 1450 or so, happened to be the place where William Outred also went to school. And at least for a while, in the accurate or inaccurate portrayal of Wikipedia, when it listed scientists who had gone to Eton College, there was William Outred was listed, and then Robert Boyle, also in the 1600s, and then there was a big gap, and then it went to me. I don't know if that's still, Wikipedia is pretty inaccurate on many things, and I have no idea whether that's even correct in that claim. But that was, for a while, kind of an amusing thing in terms of Eton has been a producer of many politicians and military folk and all kinds of interesting characters and writers and so on. But in the past, not so many scientists. And to have a gap from the 1600s to the late 1900s seemed like a pretty big gap. But to the question of who had a slide rule, what did, who used these? Leibniz could have had a slide rule. I don't think he did, because Leibniz built a mechanical calculator. I've even seen it. It was made of brass. It didn't work very well. It took him 30 years trying to sort of debug the mechanical calculator. The first mechanical calculator of modern times was probably made by a chap called Chicard, who was a friend of Kepler's. And this is in the early-ish 1600s, made kind of a sort of a gear-based clockwork-ish kind of thing for doing arithmetic computations. sort of famous version was made by Blaise Pascal in 1642-ish. And that object is still somewhere on display in Paris. Pascal had the good fortune or good foresight to make his machine out of brass, and that's something that survives. Jacquard's machine was made of wood, and it didn't survive. But by the time Leibniz was out and about, he was making such a mechanical calculator. It's an interesting question about Isaac Newton. I mean, he certainly could have had a slide rule. He certainly could have used Napier's bones, which existed by that time. I don't think one knows whether he did or didn't. And I suppose it is knowable. And in fact, like I have a facsimile of a bunch of Isaac Newton's manuscripts. I haven't looked to see how he did his calculations. I do know for Leibniz, I have looked at his calculations. And the one thing I will say about Leibniz as a calculator is that he was pretty bad at it. He was pretty good at doing algebra and pretty bad at doing arithmetic. And you find all kinds of mistakes because he would write out, paper was a valuable commodity. And so insofar as he was writing out these long calculations, they're still there on the pieces of paper that got preserved. And he was pretty bad at doing it. And I don't think it's an interesting question whether one could get evidence of whether he used something like a slide rule. I'm guessing not. But slide rules it was a very, somehow doing kind of scientific work had a certain much more manual character to it back even in the 60s and 70s. It was like, when I was using a computer that used paper tape, and it was kind of an important thing to avoid getting confetti holes in the paper tape or to be able to wind the paper tape back up again without tearing it. And similarly with a slide rule, I used to be pretty fast at doing this, of, setting up the slide rule and figuring out a number and reading it off and so on. And oh boy, this slide rule has not seen enough use. Usually the slide slides much better when it's really in common use, and you can get pretty fast at doing things. And with a slide rule, it was a much more kind of in a sense there was more hand work to be done. Nowadays you're just clicking a mouse. Let's see. Cosmic comments that their 8th grade teacher in 1983 didn't allow calculators, but did allow slide rules. Calculators came in about 1972. And I remember I got a 4-function calculator right when they came out. Maybe let's see, it must have been a year or two before that, actually, maybe 1970, that I got my first calculator. It was 71, perhaps, because I think these scientific calculators I was showing you, that was from 1972. It was funny how quickly calculators came in. I mean, by the time the microprocessor got invented and deployed in a calculator by companies like Texas Instruments and then Casio, and then there was a whole plethora of companies. I remember I had a calculator that was made in England by a company, I think, called Bowman, if I remember correctly. Right? I think it was, but it was, there was a collection of kind of diversity of companies, and that all kind of collapsed down to a small number of Texas Instruments, Casio, Hewlett-Packard, HP, and so on. But it was surprising how quickly calculators became quite ubiquitous. They were fairly cheap on the grand scheme of things, and fairly useful. Let's see. Des is asking, would you rather be stuck with just a slide rule with an abacus? I've never seriously used an abacus. I have some little abacuses, but I see people in some Asian countries, particularly, using abacuses in real life even today, and they're remarkably fast at moving things around. And I don't know how to do that. Uh, let's see. Um, uh, oh boy. Um, Question here. What my favorite artifact from the past that I own is? I think an all-time favorite, and you're going to make me go and get it in a minute, I think, um, is an object that I picked up on a beach in Sicily in 1966, maybe five, perhaps. Um, all right, why not? I have to get it. I don't know how well it'll show up on the camera. I will get this artifact. Hold on a second. Actually, not so easy. I had forgotten. Because it's my favorite artifact, it is sequestered down in an archive room, and not would take me a few minutes to extract. Maybe another time. I'll describe it. It's a piece of sandstone. It's about I don't know, a couple of inches across. Has an indentation on one side, and it's at the bottom of the indentation. It has some complicated pattern. Question is, what on earth is it? And I think I had a post that I wrote a number of years ago talking about alien artifacts and recognizing sort of purpose in objects in the solar system and so on. And I had some pictures of it there. Because here's what happened with it. So I picked it up on this beach when I was a young kid, and I was uh, I was wondering what it is. I have to say, I picked it up along with a bone. That was a leg bone of something. I didn't know what it was the leg bone of. And happily, I suppose it turned out to be a sheep leg bone and not something more sinister than that. But in any case, this thing was lying on the beach, and I I didn't know whether it was a natural object that was some kind of thing from a sea creature of some kind, or whether it was an artifact. I still don't know. Back in those days, I lived in Oxford, and I was I took it to the local. I forget which order it was in, but I took it to the local archaeological museum, the Ashmolean Museum in Oxford, and I sort of said, "Do you know what this is?" And they said, "Oh no, you've come to the wrong place. It's a natural object. Go to the Natural History Museum." So I went to the Natural History Museum, and they were like, "Nah, you've come to the wrong place. This is an artifact." So I never knew the answer. I figured that in modern times it should be possible to tell by doing molecular tests on it, and I just haven't gotten around to doing that. But that's a good favorite artifact of mine. I think maybe sometime I should give more of a tour of some of the some. Actually, I shouldn't say it's an artifact. I should just say it's an object, because I don't know if it's an artifact or if it's a thing sort of purely made by forces of nature. But yes, sometime I should give you all a bit of a tour of some of the things that I've collected over the years. And I think the um, uh, and also sometime I probably it would be fun to go through. I have about between 6 and 10,000 books, including quite a few interesting antique books, and I'd be happy sometime. It's just a question of sort of orchestrating it to give a bit of a tour of those things. It'd be fun for me. Uh, let's see. Des asks, "What's my favorite artifact from the future?" That's what I like to build. I view my life as being in large part trying to construct artifacts from the future. So there, I would say, Orphan Language and some of my theories in science are good candidates for my favorite artifacts from the future. Let's see. Quantum says, well, this is okay. Many key ideas in computer science existed before we had the hardware to implement them. For example, Turing's idea for a universal computer, or neural nets in the 1940s. What ideas today do you think are ahead of their time in the same way that we can imagine but not yet implement? We have pretty good tools for implementing things. You know, some people would say, oh, quantum computers are something we can imagine but can't implement. I don't think we'll be able to implement them either. I think they're more interesting as ways to think about organizing computations than they are as things that we can expect to one day in the future have the wherewithal to implement. I would say that one of the things that's great about computers is that sort of things which are abstract really can be concretely implemented, and it doesn't matter much the details of what kind of computer you have, what you can implement. So I think we're in a different time where most of what we can imagine along those lines, sort of at a computational level, we can implement. Now, there are things you can say, well, imagine that we could make a gravitational wave collider. Well, we're very far from being able to do that. Or imagine we could make, a black hole that was absolutely microscopic, but just sort of in the lab. Those are things that are very far from what we can do right now. And so there are many things which we can imagine at the level of physics that we absolutely can't do. There are other things where we can already see that it's implausible for us to do them. For example, if sort of a classic one is if we have a gas full of a bunch of molecules bouncing around. James Clerk Maxwell, back in the 1870s, had talked about maybe you could imagine a little demon that would be batting molecules with a cricket bat. That's been redone with other kinds of apparatus, but Maxwell was a British fellow, and so he was talking about cricket bats. And this little tiny demon would be batting the molecules when they weren't going in the right direction, or molecules were coming in one direction rather than another. And by using the cricket bat, could sort of the microscopic cricket bat could organize these molecules to sort of unrandomize a gas, kind of in violation of things like the second law of thermodynamics. Well, that's a thing where we can imagine it, but we can't implement it. And in fact, the failure to implement it is a fairly fundamental failure. If we could implement it, it would mean we could do vastly more computation than we can actually do. And so it's sort of a theoretical boundary as well as a practical boundary. We can go even further than that. In our model of physics, the structure of space-time is such that space consists of this giant network. And if we could only know sort of how to navigate through that network exactly right, we could go faster than light. The problem of sort of going faster than light is not really a physics problem. It's really an engineering problem. It's kind of like if you have molecules in a gas and you want to get from one side of a room to another, if you pick exactly the right molecule, every micron that you go, you pick the right molecule, you'll be able to kind of surf from one side of the room to the other at the speed of sound, even though the molecules are actually just hitting each other and getting randomized in direction, and things don't usually, travel that fast because the molecules are just getting, you're not picking the right molecule to sort of piggyback on. But so you could do the same thing for space-time. Well, in principle, you could do the same thing for space-time, except that there's no way to have the computational ability to kind of predict enough about what's going to happen in the universe at that microscopic scale, because actually the only thing that gets to predict that is the universe itself. You don't get to have a computer that can run in the universe and out-compute the universe itself. And so that's a case where, again, in principle, you could do it. And you could say, well, it's thousands of years away in terms of technology development, but that isn't really right, because whatever does it has to be a thing very different from us. So if you want to say, I want to go from here to there faster than the speed of light, well, that's all well and good, but it isn't going to be you who's going to be going from here to there. It would be a thing that was sort of ground down to individual elementary lengths in space-time, which is very different from us. It won't be you and your kind of consciousness that makes it from here to there faster than the speed of light. It would be this ground down thing, just like in a gas, the Maxwell's demon isn't a little creature the size of a gnat. It's vastly smaller than that. And it's something that sort of can't be implemented with sort of the way that actual creatures are made. Let's see. Going back to some questions that were asked earlier. Let's see. Oh gosh, many questions here. They're interesting. KD says, technology has progressed at an incredible rate during the last 2 centuries. That seems quite unusual relative to other periods in history. Are we bound to enter a new era of stagnation or regression, or will we just keep going? It's funny, when you look at the arc of history, you try and figure out sort of, was there progress at different times in history? I think people's view of whether progress was even a thing has changed at different times in history. I mean, the idea that there can be anything new in the world is actually fairly new. I mean, that's sort of post, it's kind of an Enlightenment type concept that you can make new knowledge. There were periods in history where people said, what's known is written down in religious texts or whatever else, and that's what there is to know in the world. We lead our lives, we do what we do, and that is something of now, but knowledge is a thing that is not being created. That's a thing that sort of existed from the past. The idea that new knowledge can be created hasn't always existed in history. And it's funny because different things you can imagine, can new knowledge be created? Can new sort of social norms be created? Can new this and that and the other be created? At different times in history, there are different beliefs about what's possible, what makes sense, and so on. We happen to be at a time when people have the idea in most parts of the world that sort of new knowledge can be created and is worth creating, and that there's sort of a correlation between sort of success for countries and people and the creation of new knowledge and new technology and so on. I think will that continue? I think that's more of a societal question than a question of sort of what is there to discover and so on. One of the things that comes out of science I've done, things like the principle of computational equivalence, kind of tells you that there will be no end to the discoveries that can be made, both in science and the inventions that can be made in technology. We'll never run out of things to invent or to discover. It could be the case that we run out of things that we care about inventing or discovering. We say, yeah, we're good. It's kind of like, I don't need to buy a new device every year. I've got, the printer that I had 10 years ago is still just fine. I don't need to invent anything new with printers. What will tend to happen, what has happened historically, is that something arises where it's like there's a new thing you want to do, and so you need a new class of devices to do it. That's what's tended to happen in the past. But it's more a question of, well, what do you want to do? The idea of doing live streaming, for example, is a comparatively new idea. And it's something where, there are things you need to do live streaming. You didn't need them before. I think that's kind of the expectation there. Now, in terms of as I say, I think the things that lead to stagnation are mostly either not a lack of belief in the idea of progress and the idea of discovering new knowledge. It has been the case that people feel that new knowledge is too disruptive. That's been a common theme at different times in history, that people have said, no, we don't want to know that. Sometimes people say that because we don't want to know that because that's a way of blowing the world up, so to speak, and better that we not know how to do that than that we discover and put lots of effort into learning how to do it, and then somebody pushes the wrong button and we do that. So that's a reason to not discover new knowledge. I think those are fairly limited cases, and that's a very tricky issue. What kind of limitations like that one should expect to have, and what things are just like that's just a stupid idea to be developing in that direction because it's too easy to cause too much trouble, so to speak. But I think in general, there are certainly plenty of examples in history and even today where people say just it's too disruptive to our political system or whatever else to know this or that thing or to talk about this or that thing. I don't happen to be a big believer in that, but it is something that gets said and gets implemented, and that's a thing that sort of prevents progress. And when you see that as sort of a cultural norm, that's going to inhibit progress happening. I mean, I have to say that a small version of that kind of does happen in fields of science and so on, perhaps more so science than technology in some ways, where, although maybe also in technology, where something becomes very popular, it becomes very big. There are these very big sort of institutional structures that say, this is the way we do this or that. This is the way we pursue this or that kind of science. That's what people will get funding for. In technology, this is the kind of company you should make. That's what somebody will invest in you for. And those kinds of things are sort of dampers on progress. And in a sense, the progress tends to happen sort of around the edges where there isn't a big institutional structure that's kind of saying this is how it works and has to be that way. I mean, I suppose in modern times, you could say if everybody just talks to their AIs and the AIs are kind of regurgitating the mean of sort of humanity, then that's another way that progress could get inhibited. And that would be kind of an unfortunate endpoint or sort of waypoint in the development of technology. But I would like to think that, first of all, the sort of theoretical possibility of discovering new things forever is something that will actually get realized in practice. Lucy asks, how would you think about cellular automata if you were born, say, in ancient Greece or Rome or Egypt or even the 1800s? Well, okay, so cellular automata are something I've studied a lot. They're kind of simple computational processes. You have in the version of them that I kind of came up with, you have a line of cells. Each one could be black or white. And you're kind of producing a succession of lines going down the page where the next line down is the color of every cell is determined by a simple rule from the color of the cell above it and let's say to its left and right. There's nothing about that idea that could not have been implemented when people first started doing things like making mosaics in ancient Babylon. The idea is simple. And it is remarkable to me that idea wasn't implemented basically until I did it in the beginning of the 1980s. And it's a strange thing because it could have been done. There was nothing sort of mechanically stopping it being done. And I've often kind of thought it would be so wonderful if one suddenly unearthed some relic from ancient Babylon that was a cellular automaton pattern. And I've really wanted to see that happen. And I've looked for all these different archaeological artifacts where that might show up. And occasionally I've had oh yeah, this might be it, so to speak. There was one of those, something from the 1400s, I think, in maybe what's now Iraq. There was a thing that I found in an art history book, was a pattern, an elaborate pattern in I think in a mosque. And it had sort of a pattern of squares. And I thought, well, maybe this is some kind of rule that was determining the squares that were showing up here. And I kind of poked around. This was in the early 1990s, kind of before the web was well developed and those kinds of things. So it wasn't quite as easy to find this kind of information. But it's like, what was this thing? And then I discovered that, well, actually, it was a verse of the Quran written in so-called square Kufic script, which was kind of a form of kind of square calligraphy that had been kind of wrapped around in is it a spiral or is it just goes round the square? I'm not sure. But in any case, so the thing that looked kind of random was just kind of this calligraphic representation, this sort of pixelated calligraphic representation of a verse of the Quran. So that didn't pan out that way. There are things like there's a very ancient kind of decoration in Syria from maybe might even be 5000 BC, maybe, I'm not sure. That's a sort of red paint in squares, and it's just not clear what it is. And, I've always wondered, is one of these going to turn out to be something determined by rules? I've looked in so many places, like I was curious to see the manuscripts of Leibniz, to see whether he had sort of things made by rules, because that's the kind of thing he might have thought about. Other people like Ramon Lull from the 1200s, another sort of candidate, although I don't think any of his original kind of writings have survived. I mean, the book he wrote has survived, but his jottings have not survived. And so there are many of these places where sort of it's kind of one almost had the idea of making patterns by rules. And in the 1800s, by 1800, Jacquard had invented the Jacquard loom and had these kind of punch cards specifying kind of motion of needles and so on to knit things. And that's a place where one again could have implemented something like a cellular automaton, but it wasn't done. Would I have thought of doing it if I'd been around in ancient times? I'm afraid I think I probably wouldn't have thought of it. I think, I came to think of it because I knew about computers, and I had the idea of following a particular rule over and over again. I would say that I would rate myself not so likely to have come up with that idea without kind of the mechanical mechanism of computers to implement it. And indeed, many of the things I discovered about cellular automata, I kind of discovered, well, by doing computer experiments. But even when I'd done experiments, I didn't really notice their significance for a while. And I had to sort of do more experiments and kind of get used to the results of those experiments. And, notably, like there's a picture in my book, New Kind of Science, of my all-time favorite cellular automaton, Rule 30, and it's a fairly high-resolution picture, has 12 million pixels in it. And I know that number of pixels is about the same as the number of stones in the Great Pyramid. 12 million is quite a lot. And certainly I, as a human, would never have filled out anything like that number of squares. In fact, I was somewhat, a few years ago, for some reason, I was filling out Rule 30 by hand, which I'd never done before. And it's very tedious. It's very, it's for a computer, it's easy. For a human, doing it and getting it right is pretty hard. Let's see. Oh boy, okay, a couple more things, and then I probably should go back to my day job here. Miles asks, is there a history of people discovering the concept of the ruliad and thinking about it from a different perspective, mathematical, scientific, religious, or otherwise? So the ruliad is something that I kind of came up with as an outgrowth of our physics project, but it's a concept that is sort of so obvious, one thinks that it should have been considered many times before, but I don't think it has been. And what it is it's kind of the entangled limit of all possible computations. Imagine that you take, let's say, Turing machines, simple models of computation. You take all possible Turing machines, you run them, and you see, well, what states do they produce? Some different Turing machines might produce the same states. That will sort of entangle the evolution of those different Turing machines. Just look at that object in the limit of all possible computations. Okay, why hadn't people thought about that before? I think the number one reason is because sort of computation is something, has been something, you kind of just reach a particular computation. It's like, can I do this one computation? Computers are things that sort of they've seemed like they take effort to do computations. the idea that you just splurt out all possible computations just seems too big, too sort of it's too extreme amount of computation, I think. Now, the idea that sort of everything can be embodied, encapsulated in this one object is an idea that's shown up over and over and over again. I mean, in mathematics, there is this notion of the infinity groupoid due to Alexander Grothendieck from the 1960s, 1970s, which actually is structurally pretty much is the ruliad, but thought about in a very different way and not in a computational kind of way. It's a thing that arises from category theory. Category theory is kind of a sort of in a sense, a model of mathematics. You know, in mathematics, you have different kinds of things you talk about. You might have numbers, you might have triangles, you might have functions, you might have different kinds of things. Category theory is a way of sort of just saying, let's think only about the kinds of things we're talking about, not so much about the details of which particular number, which particular function. So category theory has this idea of a category which has objects in it, and it has morphisms, which are mappings from one thing to another. So it might be, a morphism might be a mapping from numbers to numbers, for example, but more often it's a mapping from one kind of thing to another kind of thing. And in any case, you build up these chains of morphisms, and then you can get a little fancier. You can make up functors, which kind of map from one chain of morphisms to another one. And then you can get even fancier, and you can build kind of higher categories that are maps from that are kind of maps from one kind of set of mappings to another. It's kind of like you're saying, I've got these paths, and then I'm going to have a path as a map from one point to the next, to the next, to the next. Then I'm going to have a map from one path to another, where I take one whole path and I deform it to another path. And then I take that thing, which is sort of like a surface, and I can say, well, let me deform that surface to another surface. You keep going, and you're going to higher and higher categories, looking at the mappings of higher and higher objects. The infinite limit of that is the infinity groupoid, and that is a very similar construct to the ruliad, but reached from a very different point of view, and not reached from a sort of computational point of view, reached from this kind of limit of mathematics point of view. Now, when it comes to the idea that there is sort of an everything, that everything is one, and that, for example, everything that could be is part of that one, and that we are part of that everything, and that our perception of the world comes from our way of kind of parsing the one, so to speak. That's a kind of concept that's arisen over and over again in theology of various kinds and so on. I mean, I'm not sure that I can completely parse out, and I'm curious. In different religious traditions, for example, there's sort of the monotheistic traditions where kind of there is the one God, so to speak, and then there's the kind of the ideas that are more like people like Spinoza had this idea that kind of the universe is the thoughts of God actualized, and that kind of sort of wraps together this idea of the one thing that is sort of the God thing with the thing that is kind of the universe of all possible universes, perhaps. I don't think Spinoza was thinking that way. And, you know, I think in Buddhism, for example, there's kind of this, there are these notions of kind of sort of reaching the everything. And for me, that's sort of interesting because within the ruliad, we operate as kind of very constrained, very localized observers within the ruliad. And in a sense, as we kind of expand our reach, as we expand our kind of the concepts that we can deal with in our minds, we're kind of expanding in rulial space. And one of the things I find interesting is that kind of, I think it's sort of analogous to the Buddhist tradition of kind of when you sort of reach everything, you have sort of expanded to the point where there's no longer a coherent you to talk about. So it's kind of within the ruliad, when you expand too much, if you could reach the whole ruliad, then in a sense there'd be no specific you, no coherent entity that is the thing that you can identify as you, so to speak. So that's another potential connection. But I don't really know I think it's sort of interesting to see what are the kinds of thinking that have been done in theology, particularly before the period of modern science, when kind of science took over as kind of the thing that was explaining universe-like stuff from theology, to see what kinds of, in a sense, reasoning had been done about things like the one that is everything, so to speak. And I don't think it's very difficult for me, for example, to understand that stuff because, I know a bunch of modern science and I can sort of project backwards into, well, this concept that I can read in some way that is presented in a way that doesn't resonate with me. I mean, something like, I can read the book of Genesis and it'll be talking about sort of a story of creation, so to speak, that may have some interesting ideas that even relate to kinds of things we talk about with the ruliad, but it's couched in terms of, a 1 week mission and, snakes and things. It's couched in terms that were understandable, but don't map very well to the kinds of things that that sort of I'm used to for modern science. I mean, it has to be said that some aspects of modern science are in the future will probably seem as like bizarre ways to describe things as perhaps some of those religious texts seem to me from a science point of view as ways to describe things. But I think there are sort of interesting ideas couched in ways that are difficult to understand from a kind of modern science point of view, whether it's kind of the notion of different languages and the Tower of Babel and things like that, and the concept that there could be different languages expressing the same thing and so on. Those are interesting concepts, but it's kind of a untangling the kind of the presentation, which is very different from whatever 2,500 years ago, whatever, than it is today. Let's see, maybe one more thing here. Let's see, there's a question. Gosh, two things, and then I got to go to my day job here. Emrudo asks, I'd be interested in hearing about the bug of Alan Turing. But I think you perhaps mean when Alan Turing wrote his paper in 1936, it was called On Computable Numbers with an Application to the Entscheidungs Problem. That was the paper that introduced the idea of a universal Turing machine, the first kind of fairly easy to understand kind of device that was universal in the sense that you could fix kind of the hardware. It wasn't real hardware, it was conceptual hardware there, and feed it different programs to have it emulate different devices like Turing machines. So Alan Turing wrote out kind of the description of his, he wrote it out and he said, this is how the machine can have a description of another machine embedded in the machine. And it has at least several bugs. I've never really traced through exactly what those bugs are, but it has several bugs where it wouldn't quite work. The principle is exactly correct. The details were not. At the time, I don't think Alan Turing really had in any way conceptualized the idea that bugs are sort of endemic. I mean, people knew that mathematical proofs were hard and people made mistakes in proofs, but the idea that there would be something where the sort of you understood the big picture, but the details weren't quite right, wasn't something that was kind of part of the consciousness, I think, at that time. Danielle comments, it seems like our definitions of science and technology have evolved over the years. Are they historically the same thing? I don't think so. I think science is the attempt to take what happens in the world and kind of put it into a form that we can understand with our sort of finite minds. It's science is the story of bridging from what's out there to what we can understand in our minds for the sake of us understanding what's out there. Technology is about taking what's out there and fashioning pieces of it so that it achieves things that seem useful to us. It's about sort of going the other way. It's about taking what we think of in our minds and imposing those thoughts on the world to create things that will then do things that seem useful to us. So I think they're really sort of complementary ideas. That the science is sort of taking from what's out there and trying to understand it. Technology is about taking what we understand and sort of imposing it on the world. And it's, in my own efforts in sort of the computational universe, I've sort of done both things. Wolfram language is an attempt to do the technology side of it, to take things we think about and cast them into computational form that can then be sort of implemented in the computational universe. I've also done a lot studying programs like cellular automata that just sort of exist as natural things in the computational universe. And then it's up to us to try to take those and sort of stuff them into our minds and understand how they work. Okay, I think there are many more questions here that are interesting and comments, but I think I should wrap up and go back to my day job. And yeah, and another time, maybe I'll get out a few more artifacts or natural objects and be able to do more of a show and tell. But that was fun for me to get out a slide rule and try and remember what all the scales on it mean and so on. But anyway, thanks for joining me, and look forward to chatting with you another time. Bye for now.